So according to the equation, this P momentum is equal to BRV and MV is equal to BQR. So V over RB is Q by M. If we use the same charge particle in all atoms, then the charge constant, M constant, so V over RB constant, and this is also called the charge to mass ratio, mean the specific charge measured in coulomb per kg. So the specific charge E by M is V over RB. If same charge particle is used in all atoms, then this can be constant. So the constant is equal to V divided by RB. So we can write equation V is equal to KRB. So this K is Q divided by M. So same charge particle in our atoms. So K constant. So we can write number one, if the charged particle is same, magnetic flux density is constant, then the equation says V directly proportional to R. The larger speed will make the large radius in the magnetic field, the large radius of the circular path. And number two, if the charged particle is same, speed is kept constant, then according to the previous relation, when speed constant, K constant, then the product of RB is also constant, mean then the radius is inversely proportional to B. So stronger field will give you the small radius, more force, more bending, smaller radius in the magnetic field. And number three, same charge particle and we keep the radius constant. Okay, we want to move it on the same track. We want to keep the radius constant. Then the equation V is equal to KRB, this K constant, R constant, definitely then V directly proportional to B. If the speed becomes double, to keep the radius constant, speed on the entering must be double, and so on. Now suppose we have uniform magnetic field, which is out of the board, out of the page. Dot circle mean the blobs are representing the field directed outward. And this is any charged particle, suppose alpha, with double elementary charge, mass for U. According to Fleming left-hand rule, it is deflected downward. So the magnetic force is acting downward. But when two metal plates are placed here, one at the top and other at the bottom. This is plate A, this is plate B, and this plate is connected with the positive potential. This is connected with the negative potential. So due to potential between the plate, there is electric field strength directed from positive to negative. So this electric field will exert force in this direction. So both fields are perpendicular to each other. Magnetic field is out of the page and the electric field is towards the top of the page. Both are perpendicular. When this alpha charge particle enters, magnetic field is downward, but the electric is upward. Mean magnetic force is downward and the electric force upward. Both forces are opposite in direction. If they are equal in magnitude, then the resultant force on the moving charge particle will be zero. Yes, FB is equal to FE, but must be in the direction zero. So when resultant of the both is zero, then this moving charge particle will pass through the field undeflected. It will go straight. And this situation is called Hall's effect. So for the Hall's effect, number one, electric and magnetic fields must be perpendicular to each other. Number two, electric and magnetic forces must be equal in magnitude and opposite in direction. Mean resultant force zero, then charge particle will go straight, and this combined effect of the electric and magnetic field is called Hall's effect. So in Hall's effect, no deflection due to electric field, due to magnetic field, because the resultant force zero, then we can write magnetic force and electric forces both are equal. So the magnetic force is BQV sine theta and electric force is EQ. Now this angle theta is 90 degree. So we can write BQV is equal to EQ when Q cancelled. So the product of magnetic flux density and the speed is equal to electric field strength. And then this V is equal to E divided by B. So for the Hall's effect, this ratio is very important. It is the ratio between electric field strength and the magnetic, and this is called velocity selection equation. Mean which magnitude of the velocity must be selected for the Hall's effect. First calculate the ratio between electric and magnetic field, then select the velocity equal to that ratio. So definitely the moving charge particle will follow the straight path due to the Hall's effect. And this is called velocity selection equation. V is equal to E over B. Now, E is equal to B times V, and this electric field strength is electric potential divided by distance, B into V speed, and this potential V, which is provided to the plate, is called Hall's voltage. After the Hall's effect, it is Hall's voltage. So the Hall's voltage VH is B, V, and D. B is the magnetic field strength in Tesla, and V is the speed with which the particle enters perpendicularly, and D is the distance between these two plates, the gap between positive and the negative plate. So Hall's voltage is equal to B, V, and D. Now, this is very, very important for the calculation. Okay, now the application of Hall's effect. Suppose we have crystal oxides of periodic table fourth group element, germanium, bismuth, antimony. So this is a crystal. It is in the form of cube or cubide. Now, it is connected in a circuit with the help of the araldite connections. These two sides are connected with the circuit. These are the wires. It is a semiconductor. So the sensitive ammeter, either milliammeter or microammeter, is connected with it. Here is a switch S, which is open. And for a significant current, a large DC battery is connected with it. When switch S is closed, current flows through it, so ammeter reader. Suppose it is a positive charge carrier. It is p-type crystal, so the positive charges are flowing in this direction and reaching to this terminal, completing the circuit, and current is there. Speed of the charge particle inside the crystal, inside the wire, is called drift speed. So drift speed, from the formula A1, we can write I is equal to eta QAV. So the drift speed is equal to I divided by eta QA. This is the drift speed. I is the current. A is the area of the phase through which the current is entering, mean this area. And Q is the charge of the particle which is flowing. And N is the number density of the electron, mean number of the charge carrier per unit volume. So the charges are flowing with this drift velocity, drift speed V. When a magnetic field is placed here, or magnetic field is introduced here, perpendicular to the direction of the motion of the charged particle, like this. Suppose this is the direction of the magnetic field in the Tesla, and it's making this angle 90 degrees. Mean this side North Pole at the back, here the South Pole. So this is the direction of the magnetic field. According to Fleming left-hand rule, this charge particle is deflected up. Look, field into the page, into the board, current towards right, so the deflection up. So this charge particle is deflected up instead of reaching here, so it stops here. No charge is reaching on this terminal, so the current becomes 0. So when magnetic field is placed perpendicular to this semiconductor carrying current, the current becomes 0 because the charge is deflected up. Battery is still connected. When the second charge will come up, right, from the battery, so it is also deflected up. Similarly, all charges are deflecting up. Being neutral, this crystal was neutral. When the positive charge will appear at the top, automatically negative charges will appear at the bottom. And due to stationary charges at the top, stationary charges at the bottom, an electric field is developed from bottom to top with electric field strength, suppose E. So when magnetic field is placed perpendicular to the direction of the current, an electric field is produced with the help of the magnetic field. Now, when there's a sufficient electric field there, then two forces, magnetic force up, but this positive and this negative gathering of the charges will also exert force downward, which is electric. When up and down forces, up magnetic force due to magnetic field, down electric force due to electric field becomes equal, resultant force 0, then no net force experienced by the next moving charge. So it goes straight due to the Hall's effect. When it reaches next time on this terminal, circuit completes and current flows. So for the short period of time, the current will disappear. But when next time when the current appears, when the current flows, meter reads the current, it means there is 100% Hall's effect in the crystal. So Hall's voltage is equal to BV into D. Hall's voltage is equal to BV into D. And what is D? D is actually this side. It is the distance between positive and negative plate, mean this one. Now, Hall's voltage in this case will appear B, the drift velocity formula is I divided by eta Q A, and the area is length into width times D. So we have to calculate the area. Look, the calculator of this face, which is carrying the current. So this is the thickness and this is the D. So we can write VH is equal to BID over number density Q and T into D, because the area is length into width, T into D. The D is the height, distance between the distance between the two charges, positive, negative, and T is the thickness, not time. So this D is cancelled. So the Hall's voltage now is B times I divided by number density charge into T thickness of the crystal, not the time. So from this, number one, we can write Hall's voltage developed in the crystal is directly proportional to B. Number two is directly proportional to I. And number three, it's inversely proportional to the number density. Number four, it inversely proportional to thickness of the crystal, and so on. Now, this is the formula to measure, to calculate the Hall's voltage. But if it is directly measured from the instrument, then we will definitely connect a voltmeter. Yes, one lead of the voltmeter is connected at the top, other at the bottom, and then this is connected with a voltmeter. So this will give you the Hall's voltage. So the 6 sides, this and this for the current, front and back for the magnetic field, top and the bottom for the Hall's voltage. So 6 sides of the crystal are occupied. Now, this Hall's voltage directly proportional to B. When the field is strong, yes, more Hall's voltage. It's directly proportional to current, but look at this. If the number density is large, mean if the crystal is of good conductor material, it has more free electrons per unit volume, then the Hall's voltage will be small. It means for the bad conductor, Hall's voltage will be more. For the good conductor, right, the Hall's voltage will be small. Inversely proportional. Number density and VH both are inversely proportional, right? Suppose we place here the piece of the copper, cube of the copper, we connect. Copper has high number density of the electron due to its good conductivity. So voltage, Hall's voltage will be small. But if crystal is placed here, glass crystal placed here, which has less number of the free electron, small number density of the electron, it will give the large voltage. And similarly, it also depends on the thickness, but inversely proportional. Now, this voltmeter, which is connected between the top and the bottom, when no magnetic field is introduced to the crystal, the pointer of this voltmeter will be at 0 Hall's voltage. And when magnetic field is placed perpendicular to the flow of the charge, flow of the current, perpendicular, then it will give you the maximum reading in the crystal. If the field magnetic, which is placed perpendicularly to the current, is of the known value, for example, 100 millitesla, no field, no voltage. So instead of voltage, if we write here 0 millitesla, and instead of the voltage, if it is calibrated into 100 millitesla, look at this, voltage and B both are directly proportional. So directly proportional means this scale must be the linear. Then this middle value will give you the 50 millitesla. This will give you the 25 millitesla, 75 millitesla. So if voltmeter is calibrated into Tesla with the help of the known magnetic field, then the whole instrument is called Hall probe, which is used to measure uniform magnetic flux density B. Then the whole instrument is called Hall probe. If this voltmeter is calibrated into Tesla, then this device is called Hall probe, which is used to measure uniform magnetic flux density B. Similarly, in thermocouple thermometer, voltmeter was calibrated into degrees Celsius. In car speedometer, voltmeter is calibrated into kilometer per hour. So this voltmeter is calibrated into Tesla, so it is converted into the Hall probe, which is used to measure only uniform magnetic field. But after calibration, if this Hall's voltmeter, this voltmeter is disconnected from the circuit and it is connected with a coil. This is calibrated in Tesla voltmeter. But here it is connected with a coil, then this coil is called surge coil. If any coil is connected with a voltmeter but calibrated into the Tesla, that coil is called surge coil, and it is used to measure non-uniform magnetic field. Reason? Non-uniform magnetic field will be cut by the coil. According to Faraday's law of electromagnetic induction, an EMF is induced and that induced EMS will appear on the voltmeter, but the voltmeter is measured in Tesla. So instead of the voltage, it will give you the strength of the B in Tesla. So this instrument, which is the Hall probe, measures only uniform magnetic field, but when its voltmeter calibrated connected with the coil, it is called the search coil, and it is used to measure non-uniform magnetic field on the principle of electromagnetic induction. This is suppose any crystal. And it's p-type. Positive charge is flowing in this direction. When the magnetic field is introduced in this direction, so this charge particle deflected up, this side becomes positive, this side becomes negative. This is the case when this is positive charge carrier. But some crystals are negative charge carrier, they are N-type, then the negative charge particle is moving in this direction for the conduction of the current. So when magnetic field is introduced, according to Fleming left-hand rule, this negative charge particle also deflected up. So what's the difference? Top becomes negative and the bottom becomes positive. So the force on the both p-type and n-type charge carrier will be same up, but the difference will be for the first voltage, Hall's voltage will be positive, and for the other, the Hall's voltage will be negative, because this is positive, this is negative. So when Hall's voltmeter connected here, so this will give you the positive, and then for this will give you the negative potential. So the negative charge carrier, the positive charge carrier will be deflected in the same direction for the same magnetic field, but they will give you the different polarity of the Hall's voltage, because for one top becomes positive, for the other top becomes negative.